Every single minute a stroke goes untreated, the human brain loses nearly 2 million neurons. It is a race against a clock that never stops. And right now, the biggest bottleneck isn't the medicine, it's the wait for a diagnosis. In a crowded emergency room, getting an MRI is only half the battle. The real delay happens while that scan sits in a queue, waiting for a human radiologist to spot a needle in a haystack of gray pixels. But researchers at the University of Michigan have developed a system that might just change the game. It's called Prima, and it's doing something that was previously thought to be years away. Prima isn't just another AI model. It's a specialized architecture designed to interpret complex brain MRIs with a level of precision that is frankly staggering. We're talking about a system that can see what the human eye might miss in the heat of a crisis. The goal here is simple: rapid triage. By identifying potential strokes and neurological conditions in seconds, Prima can move the most critical patients to the front of the line before the damage becomes permanent. And the results? They're hard to ignore. In initial testing, Prima achieved an accuracy rate that has the medical community buzzing. But how does it actually work under the hood? To understand Prima, you have to understand the data. The University of Michigan team didn't just feed it generic images. They used a massive, curated dataset of real-world clinical scans to train the system on the messiness of actual emergency medicine. This wasn't just about showing it what a stroke looks like. It was about teaching it the subtle variations in brain anatomy that differ from person to person. It's a masterclass in pattern recognition. But the real headline is the number: 97.5%. That is the accuracy Prima achieved in interpreting these scans. In the world of medical AI, that's not just a step forward, it's a leap. Think about that for a second. 97.5% accuracy in a field where every percentage point represents a human life saved or a disability prevented. It's one of the highest benchmarks we've seen for this kind of complex task. But accuracy in a lab is one thing. Accuracy in a chaotic, high-pressure emergency room is another. That's where the architecture of Prima really starts to shine. It's built for speed without sacrificing reliability. So, how did they do it? How did they build a system that can outperform traditional methods while running on standard hospital hardware? The answer lies in the way Prima processes information. We're about to dive deep into the technical layers of Prima, from how it handles pixel-level data to the way it makes its final decision. And trust me, the engineering behind this is genuinely brilliant. But as impressive as the tech is, it's not perfect. There are critical limitations that doctors have to navigate every day, and if we ignore them, the consequences could be serious. Before we get to the risks, let's look at the engine. Let's see how the University of Michigan built the most accurate brain scanning AI in the world.
At its core, Prima is a deep learning system, but it's not just a standard black box. It uses a multi-layered approach to analyze MRI slices, looking for features that are often too faint for standard software to flag. The architecture is optimized to handle the high-dimensional data of an MRI. Instead of just looking at one image, it looks at the relationship between different slices to build a 3D understanding of the brain's condition. This spatial awareness is key. It allows Prima to distinguish between a genuine blockage and a simple anatomical variation. It's this nuance that drives that 97.5% accuracy figure.
The training process was equally rigorous. The Michigan team used ground truth labels, diagnoses that were confirmed not just by one doctor, but by a consensus of experts, and follow-up clinical outcomes. This high-quality training data is the secret sauce. By learning from the best possible examples, Prima avoids the garbage in, garbage out trap that plagues many other medical AI projects. And because it was developed within a university hospital system, the developers had direct access to the feedback loops necessary to refine the model's performance in real time. But here is where it gets really clever. Prima is designed to be hardware agnostic. It doesn't require a multi-million-dollar supercomputer to run. It can be integrated into existing hospital IT infrastructure. This means a small community hospital could theoretically have the same diagnostic power as a major university center. It levels the playing field in a way that could save thousands of lives in rural areas. The processing speed is also a major factor. While a human might take 20 minutes to thoroughly review a complex case, Prima can provide a preliminary analysis in under a minute. Now, some skeptics might ask, isn't this just another black box AI? If we don't know why it's making a decision, can we really trust it with a patient's life? The Michigan team addressed this head-on. Prima includes explainability features. It generates heat maps that show radiologists exactly which parts of the image it's focusing on. It's not just saying there is a stroke, it's showing you where and why. This transparency is crucial for building trust. It allows the physician to remain the ultimate decision maker, using the AI as a powerful second set of eyes, rather than a replacement. But even with all this brilliance, there's a catch, and it's a big one. The very speed and accuracy that make Prima so impressive also create a new kind of risk, one that hospitals are only just beginning to understand. We're talking about automation bias and the loss of clinical context. Because, as it turns out, a 97.5% accurate image scan isn't the same thing as a 100% accurate diagnosis. Next, we're going into the ER to see how Prima actually performs in the real world and why the biggest danger might not be the AI failing, but the humans trusting it too much.